Welcome and hello. This is a video exercise in HY-8, and this exercise we're going to be dealing with internal energy dissipators. So we're going to have a culvert set up and a maximum allowable velocity, which we will need the help of a dissipator to achieve. All right, so let's go ahead and get started. What I have on the screen is my HY-8. First thing I'm going to do is switch the unit system to metric, so SI units if you don't already have that set. Next, let's go ahead and create a crossing. So new culvert crossing is our selection from culvert menu. That'll bring up this dialog box here where we provide the crossing data and the culvert data. After that, we'll get a calculated outlet velocity, and we will have to use an energy dissipator to slow down that flow. All right, as a quick introduction, I'm going to bring up a PowerPoint here, and this shows the data for our problem, at least some of it. Our design discharge is going to be 5 cubic meters per second. The minimum freeboard is 2 meters. So as you can see from the diagram, we have a roadway with an elevation at 56 meters. And then due to the minimum freeboard of 2 meters, that puts the maximum allowable water surface elevation at 54 meters. The culvert shape we're going to be using is a box culvert, a box concrete material culvert that's 1.5 meters wide by 1.0 meters high. That's the rise. Culvert length will be 10 meters. It'll drop from 50.1 at the upstream end down to 50.0 on the downstream end for a total slope of 1%. The cross section that we can fit our culvert barrels into is trapezoidal here with a 5.5 meter base and a side slope of 2 horizontal to 1 vertical. It looks a little bit backwards, but that's just because the scale is off, as you oftentimes see in diagrams like this. All right, the culvert length is 10 meters. I said that. Max outlet velocity of 2 meters per second. This is the design requirement that we're going to need the help of the internal dissipators to achieve. All right, so with this data in mind, as well as some other data, let's get started on filling out our crossing data for crossing 1. All right, I'm going to leave the discharge method as it is, minimum, design, maximum. And then for minimum flow, I'll leave that at 0. The design flow, which we have as 5 CMS, and then the max flow, I'll just set that to 10. So we have a nice even range from 0 to 10 with a step of 1. All right, the tailwater data section we need to complete next. Channel type, I'll switch that to trapezoidal. The bottom width, we know that is 5.5 meters from that diagram. The side slope is 2 to 1, also from the diagram. We're going to use a channel slope of 2%, so 0.02. Manning's N will be 0.035, and then the channel invert, I already said that would be 50.0 because this is the downstream end of the culvert. If we want to look at the rating curve, we can click on View and then Plot. We see as the flow rate increases from 0 to 10 CMS, the water surface elevation in that tailwater channel is 50, increases to 50.6 approximately, 50.596. Okay. Next, we need to provide the roadway data. So we'll just start the stationing at 0. For a crest length, I'll go ahead and say that's 30 meters. And then an elevation, we know that's 56 meters. Remember, we have the 2 meter is the minimum freeboard. And then for top width, I'll say that is 7 meters and tab off. Okay, so we're done with our data, our crossing data input. Next, let's go ahead and define our culverts. We're only going to have one culvert, but we're probably going to have more than one barrel. Let's start from the top, though. We'll call it culvert 1. It's going to be a shaped concrete box. The material's concrete. That's our only option. And then the span, we're entering the units in millimeters. So 1.5 meters would be 1,500, and then 1 meter tall would be 1,000 millimeters. We'll say 0 embedment depth, and then Manning's N will be 0.012. Culvert type will be straight, and the inlet configuration will be square edge, 90 degrees. Inlet depression is no. All right. Last part of this input is the site data. This is the actual culvert dimensions. We'll say that it starts at 0. The outlet elevation or outlet station will be 10 since the length is 10 meters. And then we already have the inlet elevation is 50.1 and the outlet elevation is 50.0, which matches the elevation over here for the channel invert elevation on the tailwater end of the culvert. Okay, there's that 1% slope that we're talking about. Let's go ahead and take a look at our numbers and the velocity and headwater heights specifically, because those are the two requirements we have. When we look back at the notes, the minimum freeboard is 2 meters, which means 54 meters is our max headwater, and then the max outlet velocity is 2 meters per second. So those are the two requirements for this design. I'm going to click on Analyze Crossing. Here is the data. Now we're specifically going to focus in on this row right here with 5 CMS. Looks like our headwater is 52.35, so that's good. That's below 54 meters. So if I click on Close, we should see the image here. If I click on Culvert, right. So the headwater elevation, 52.3 or 52.4, whatever I said, well below 54 meters. So we're safe there. I'm going to go back to the data. And then instead of crossing summary table, I'm going to click on culvert summary table. Again, I'm focusing on the 5 CMS row. Specifically over here on the far right, the outlet velocity is 3.75 meters per second. And one thing we can do to actually slow that down, I think, is to increase the number of barrels. So I'm going to click close here. Oops, go back to the design and actually go back to the notes. So we have 5.5 meters of width, but if each culvert barrel is 1.5 meters, then we can actually fit 3 barrels in, unless I stacked a separate row at a higher invert. But let's just go with that. Let's just try to fit 3 barrels in and see how much slower the outlet velocity is, as well as check the freeboard or check the headwater elevation. Same idea. So I'm going to go back to my data input, change this 1 barrel to 3 barrels and hit tab, then click Analyze Crossing. All right, so the headwater at 5 CMS is now 50.7. Okay, that's even less. That's not even a submerged inlet anymore. We could actually check the flow type by clicking on Culvert Summary Table. Here is our row for 5 CMS. And then the flow type is right here, 1-S2N. I'm pretty sure that's type 1. If I click on the flow types button, 1S2N is inlet controlled. Okay, very cool. I'll close that up. But what I'm more interested in is this outlet velocity, 2.79 meters per second. So that is a problem. That's what we need the internal dissipator for. We want to get this number down below 2.0 meters per second. And at the same time, we want to make sure that our headwater does not exceed 54 meters in elevation. So let's click on the energy dissipation button down here at the bottom. This brings up the energy dissipation dialog box. The first decision we need to make here is up at the top. Estimate scour hole geometry is not what we want. We want to click on Design Internal Dissipator. All right, first we need to select our culvert crossing and flow rate. It looks like that is already set. This is our one and only crossing, our one and only culvert, and the design flow rate looks like it's defaulted to our design of 5 CMS. So that's all good to go. We see our outlet velocity of 2.79. We already saw this number earlier, but what we want to do is get this below 2.0. And we will do that with the help of our internal energy dissipator, which we get to select the type right here. Let's go with increased resistance. Now in your own designs, you're welcome to use different types and input different data. But I'm going to use increased resistance and play around with that one. Scroll down to make sure that we meet the special limitations, which basically means we have to be using the shape of a concrete box or circular. That's correct. We're using a concrete box shape for our culvert shape. And then the two input fields that we need to provide values for is this roughness element height to hydraulic radius ratio, H divided by R, and then also the height of the roughened section itself, like the baffles, you may call them. All right, I'm going to start small. I'm going to say 0.1. The range is 0.1 to 0.4 here on this roughness element height to hydraulic radius ratio. And then for, so whenever you click off, it likes to scroll you up to the top, which is a little bit disorienting. So here we are, 0.1. I'm going to go with 0.3 meters. Remember, we have a 1.5 meter wide culvert and it has a rise of 1 meter. So I think 0.3 meters would be good, but we can adjust that as well. All right, so if I tab off of that, of course, it sends me to the top, but I need to scroll down here. I can see my results. Exit velocity, we're already down to 2.034. So that's really good. That's a good improvement because before we started at 2.79. When we added the increased resistance type internal dissipator, now the outlet velocity is down here at 2.034. We're almost there. We just need to get below 2. It looks like the spacing for this design was 0.349, which means that there's a baffle every 0.439 meters. So along a total culvert length of 10 meters, it should give us the number right here. Number of rows, 19 separate baffles. Okay, good to see that. Let's go ahead and modify our numbers up here to try to get below 2.0 meters per second on that outlet velocity. Instead of 0.1, I'm going to increase this to, how about 0.2? Remember, we don't want to go over 0.4. So if I click off of that and then scroll down to the results, I'm looking for exit velocity. Ah, there we go, 1.907. So that's good to see. Mission accomplished. We've achieved our maximum velocity requirement by getting it under 2. Just out of curiosity, I'm going to change this one more time. Let's go up to 0.3 on this ratio. So 0.3 and 0.3, and then scroll down. Yeah, 1.791. So it looks like we have more room to improve, or I should say further decrease that exit velocity at our design flow rate of 5 CMS. In fact, we could even check some higher designs since we finished kind of quick, some higher flow rates. If you change this number right here, say to 10 CMS, unfortunately, the numbers don't get updated right here. So what I've found in HY-8 is what you need to do is actually go back to the input data, change the design flow to whatever you want to actually use for your energy dissipator. So if I'm interested in designing for 10 CMS, I could just put 10 CMS right here, tab off, let it calculate, then click on the energy dissipation button, and it has 10 CMS here. But what's more important is it actually has the data right here for 10 CMS, such as 3.36 meters per second. Okay, let's go ahead and see what sort of decreased exit velocities we can get for a 10 CMS flow using internal dissipators. Right here, it's 0.3 and 0.3. So if I calculate that, it looks like it drops down to 2.252. That's incredible. That's like a significant decrease right there. But anyway, I'm going a little bit off topic. I'm going to click on the Analyze Crossing, and at 10 CMS right here, it looks like the headwater is 51.53, so that's also well below the requirement of 54 meters. All right, well, that was it for this exercise. What we talked about was the internal dissipators within HY-8, and we were able to reduce the outlet velocity from 2.7 down to below 2.0. That's in meters per second for this particular design.